All right, starting lesson 1.5, the distance formula. All right, to start off, a prime, is a number that is only divisible by 1 and itself, with the exception of the number 1. So what's the first prime? And it's the only even prime. It's 2. All right, then the next one is 3, and then 5, and then 7, and then 11, and then 13, and then 17, and then 19, then 23, and it just keeps going. All right, now the square root, here we have the symbol for the square root. This is the same thing here. Now square root is used so often that very often they'll omit the 2 for this particular radical. All right, square root is the most common radical used in geometry. If you're taking the square root of a number that is not a perfect square, then you must use the prime factor tree. Now, what is a perfect square? A perfect square is a number that could be broken down into 2 numbers that when multiplied, you get that number. So for example, 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25 is a perfect square, and so on. Okay, because you could find a number times itself that gives you that particular number. All right, simplify the radical. So 25 is a perfect square. So what times itself is 25? That's just 5. All right, now we have the square root of 20. All right, is there a number times itself that's 20? No. So in this particular case, we have to break this down using a prime factor tree. Now, what's the smallest prime that goes into 20? 2. 2 times what is 20? 10. Now, since 2 is prime, we don't mess with that anymore. Is 10 prime? No. So we could break it down. Smallest prime that goes into 10? 2. 2 times what is 10? 5. All right, now this is why it's called a prime factor tree, because at the ends of all the branches, you have primes. All right, so we're looking for a pair of primes. Here I have a pair. Okay, so whatever I have a pair of, I pull that number out. That's 2. And then left inside the square root is whatever I have left over, 5. That's all there is to it. We're done. All right, going on to C. What's the smallest prime that goes into 48? 2. 2 times 24. Smallest prime that goes into 24, 2. 2 times 12. Smallest prime that goes into 12, 2 times 6. Smallest prime that goes into 6, 2 times 3. All right, so I have a pair of 2's here, and I have another pair of 2's. So this is equal to 2 times 2, and then the square root of 3. So I end up with 4 square root of 3 as my simplified result. All right, 96. 2 times what? 48. Then we have 2 times 24, 2 times 12, 2 times 6, and 2 times 3. Now notice that I'm always using the smallest prime, because if you don't use the smallest prime, then you get a tree that has branches all over the place, and then you're going to start losing your primes and get the wrong answer because of that. But if you always use the smallest prime, then all the numbers will line up nicely in the end, as you see this. So here we have a pair of primes. Here's a pair of primes. So we pull out 1, 2. We pull out another 2. What's left inside? 2 times 3. So we have 4 square root of 6. Okay. Now for 180, we have 2 times 90. Then we have 2 times 45. Then we have 3 times 15. Then we have 3 times 5. All right, so I have a pair of 2's. I have a pair of 3's. What's left inside? 5. So I end up with 6 square root of 5. Done. All right, for the next one, I have 2 times 180. Then I I have 2 times 90, 2 times 45, 3 times 15, and 3 times 5. So I got a pair of 2s, then I have a pair of 3s. So I'm going to have 2 times 3, and the square root, I have 2 times 5. So I end up with 6 square root of 10. All right, that's all there is to it. We're done. If a segment is running horizontally, left and right, or vertically, up and down, on a coordinate grid, then you can count its length. All right, so here we have a segment running horizontally, and I could count its length. So every gap is a unit, so I have 1, 2, 3, 4, 5. All right, so that segment is 5 units long. And for this one, I have 1, 2, 3, 4, 5, 6, 7. All right, so that segment is 7 units long. You can not, however, count the length of a segment that runs diagonally. All right, I've seen students do this before. 1, 2, 3, 4. Nope, that does not work. All right, so you must use the Pythagorean theorem to figure out that length, or the distance formula, which we're going to get to next. All right, so the distance formula. Here we have it. Why I don't have parentheses around this, I don't know, but they should be there. All right, so the distance formula, you have 2 points. We're trying to figure out the length of this line here. And I have 2 points, which are the endpoints of this segment. And here's the formula to figure the length out. Now this formula actually comes from the Pythagorean theorem. All right, so here we have a right triangle. And this length here is just the difference of the x's. And this length here is simply the difference of the y's. Okay, if we square those and then we add them up, eventually we'll get to this formula. Okay, so finding the blank between 2 endpoints is the same as finding the blank of a segment. So finding the distance between 2 endpoints is the same as finding the length of a segment. All right, so for part A, find the distance between the endpoints, x, y. All right, so this is going to be my x1, that's my y1, that's x2, that's y2. All right, now using the formula, all right, I have x1, which is 1, minus x2, which is negative 2. All right, be very careful with these negatives. The negatives is where students goof the most. Then I have y1, which is 7, minus y2, which is 3. All right, so now I have 1 plus 2 squared plus 7 minus 3, so that's 4 squared. Then I end up with 3 squared plus 4 squared. End up with 9 plus 16, which is the square root of 25. And the square root of 25 is 5. Okay, xy is equal to 5. Done. All right, let's do one more example. I got x1 and y1, and I have x2 and y2. All right, so I have x1, which is negative 2, minus x2, which is 3, plus y1, which is 2, minus y2, which is negative 10. Okay. So now I have negative 2 minus 3, which is negative 5 squared, plus 2 minus negative 10, which is 12 squared. So end up with 25 plus 144. That's equal to the square root of 169. which is 13. So AB is equal to 13. Done. All right, now find the length of CD given these points. All right, a little more practice now. Should be getting the hang of this at this point. So that's x1, y1, x2, y2. So we plug in x1, which is 2, minus x2, which is 4, plus, and then I have 3 minus y2, which is negative 1, squared. Okay, so I end up with 2 minus 4, which is negative 2 squared, plus, I got 3 minus negative 1, so that's 3 plus 1 squared. So I end up with 4 plus 4 squared, and I end up with 4 plus 16, so I end up with the square root of 20. All right, and now going back to what we did in the very beginning of the lesson, let's simplify this. 2 times 10 and 2 times 5. I have a pair of 2's, so CD is equal to 2 square root of 5. Done. All right, last example. I have x1, y1, x2, y2. Okay, so I have QP is equal to the square root of x1, which is 7, minus x2, which is negative 2, plus y1, which is negative 1, minus y2, which is 6, equals, so 7 minus negative 2, which is 7 plus 2 squared. Then I have plus negative 1 minus 6, which is negative 7 squared. So I end up with 9 squared plus negative 7 squared. So I end up with 81 plus 49. And that's going to give me, what, 130? All right, breaking down 130, what do we get? 2 times 65. Then I have 5 times 13. All right, so there's nothing I could do there. There's no pairs. So QP is equal to the square root of 130. And we are done. If you have any questions, make sure to ask. Begin the assignment.